Good morning, everybody. So I guess we'll get started with this next session on flares. We have 1, 2, 3, 4, 5, 6. We have 6 talks this morning, and the first one is by Sasha Kosovichev, who's going to talk to us about chromospheric evaporation and plasma dynamics of a solar flare from IRIS. Thank you.
Thank you, Lindsay. Good morning, and I'd like to present some results of these results obtained by a group of 6 people, 3 different countries, and most of the work was done by the second author here, Vyacheslav Sadikov. Unfortunately, they were not able to come here. So the problem that we try to look using IRIS data is essentially what we can learn about the solar flares in terms of testing a standard solar model. I discussed many times here already at this meeting that the standard solar flare model is extremely simple. It just you assume that there are some particles accelerated by some mechanism, the corona. They propagate downwards along magnetic field lines, and then they stop, they hit chromosphere, upper chromosphere, creating high pressure region, and then this high pressure region expands upwards and downwards. And upward expansion is called chromospheric evaporation. And also it's a downward, you need to conserve momentum. It's photospheric shock waves. And it's one of the mechanisms also generates sunquakes. That's one of our interest. So it's originally this is SIG target model was suggested by John Brown and also Hugh Hudson. They look at static model, and then hydrodynamic model was first calculated by Kostyuk and Picklinger in 1975. And that yesterday we had a very nice tutorial on further development of this model. And it was interesting, then I look at my publication. I was a PhD student. I did similar calculations. And this was paper published in 1981 in solar physics. And the curves look very similar to what we saw yesterday. So that here that you can see evaporation. In this plot evaporation, it's a plasma of 10 million degrees. And with velocity, they can reach 1,000 kilometers per second when flux tube is open. And the downward velocity is about 100 kilometers per second, and they decrease very rapidly when the shock wave propagates downwards. So we're interested in looking at that what if this can happen in solar, we can see in IRIS data. And later, the people, they separated 2 regimes of chromospheric evaporation, that explosive evaporation that I showed in the previous plot, when plasma expands with supersonic velocities. And there is also gentle evaporation that was first suggested by Antiochus and Starek, that if you hit slowly plasma or a big electron beam, then evaporation is with subsonic velocities. That essentially this separation is supersonic or subsonic. It separates 2 regimes, explosive and gentle, and George Fisher did calculations of both of them in 85. And then there was actually that, and Lindsay mentioned yesterday, that was SMM, observed evaporation, and then actually detailed studies on SOHA, CDS, on Ryan Milligan, and that actually observed both of 2 regimes. So what we look at, we wondered what we can learn from IRIS data and selected one flare event. It was M1 class flare. And the main reason why we look at this flare, because we also observe it at Big Bear Solar Observatory. And we're still analyzing Big Bear data. And I mostly focus on IRIS data today. So the flare happened in delta type sunspot. It's around neutral line, so it was a kind of classical flare. And I show also movies from Big Bear. And Big Bear, we have a very, very interesting dynamics around the neutral line during the flare. This is a photospheric titanium oxide line. And we also have H-alpha. This is scent of H-alpha. And for IRIS, IRIS observed in coarse in coarse mode. It's with 8. The slit was it was scanning. It was 8 position of the slit, and so we have kind of a low resolution in this direction, torque second resolution in the horizontal direction, and 0.3 arc second in vertical direction, and it was covered part of the flare. It didn't cover the whole flare, but it covered it. That also a very interesting part, including the flare kernel. So this is a movie of flare that is in it's carbon-2 line. And if you look at carefully at this movie, you can notice that was a jet coming from here that before the flare. Was interesting dynamics. And about 20 minutes before the flare, and from this loop region, we observe a jet, and lasting for about 15 minutes, and it consisted of several ejections. So we don't know what it is, what the origin of the jet, and but since we have the jet was moving here from this loop-like structure in this direction. And so we selected just a point and look at, it was a typical point, and we look at the line profiles. Here you can see it's magnesium, carbon, and silicon. And the jet, you can see that it's red wing. You can see it's broader, or even you can see a separate peak. In this, it corresponds to 100 kilometers per second. The plasma flow. So we don't know what causes this jet. Is it some downflows from reconnecting region? So that but it's definitely something that is not predicted by the standard model. At least we don't know if it's typical or not. Then we look at the second result. That we look at that impulsive phase of flare. Here you can see this complicated plot. It shows several curves here, and you can see the GOES. It's this curve, this smooth curve, and then it's a different curves here than RESI. We analyze RESI data. It in the energy band from 12 to 25 keV, and here it's green areas where we did reconstruction of RESI images. And here that arrow shows where these plots, that snapshots. So here it's a kind of two-dimensional image of, but in fact, here in horizontal direction we have only 8 points. So we interpolate it, so we have a high resolution in vertical direction and low resolution horizontally. So we just smooth it to make it's like a two-dimensional image. And each of these images, it's the intensity of carbon-2 line, carbon-2K line. It just corresponds to this box. Each of these images. So what we can see in the impulsive phase, we can see this strong brightening. It's a point-like brightening, and it corresponds very well to the hot X-ray sources. So then that's interesting that the history of line profiles. I don't have time to describe it in detail, but what's interesting that if you look at this was for oxygen 1 channel of IRIS. And in this channel, this hot line appeared, iron 21 line. And it appeared, what's interesting, it appeared 6 minutes after the impulsive phase. So this one of the puzzles that what we discussed. But what's interesting that the chromospheric evaporation, it predicts that you have, if you have explosive evaporation, you have a blue shift of hot lines and red shift of cool lines. And indeed in carbon-2, it corresponds to, I don't know, 10,000 kelvins. You can see the red shift, but it was before flare and continued during flare. It's a bit enhanced, it's a bit high velocities during impulsive phase, but it was stable, so it was not related, really this red shift was not related to the flare energy release itself. And then it's already mentioned that it's interesting result that what we, it's curious, it was also observed before, that the peak of intensity of iron 21 appeared well after the impulsive phase of flare, 6 minutes after the flare. So this is a RESI X-ray from 12 to 25 keV, and this is iron 21 line. So what then we look at the maps. So here, because of this scanning mode, RESI mode, it's not sit and stare mode, we can actually reconstruct the special picture of this of the Doppler shift of this line, iron 21 line, and you can see here that overlap is these control lines. It's from RESI, and here that the white contours are for 12 to 25 keV. There was no higher significant high energy emission in this flare, and the gray contours they correspond to the lower from 5 to 12 keV. So we can see the kernels that initially the X-ray that had two kernels here, and the blue shift in this line appears at the same kernels, but then it was kind of a loop-like structure. It was filled in with evaporating plasma. So then we look at what could be energy sources of the flare. So we also did RESI spectroscopy and tried to fit two models. One model was a combination of thermal and non-thermal. This using standard SolarSoft software. And another model was a two-temperature model with, I think, 7 and 25 megakelvins. And both of these models, they fit basically equally well, the data. And then the two scenarios come to how operation can be driven, what energy sources. So the first we concluded that since we observe subsonic velocities about 50 kilometers per second in this hot line, then perhaps we observe gentle operation, and this in classification of that was first suggested by Antiochus and Starek. And they suggested that in this case heating can be by not by electrons but by heat flux, and we estimated the heat flux, and it's 10 to the 28 ergs per second. And if you estimate the heating by electrons, it's a similar value that from these RESI models. So by the way, that's estimated energy flux is 10 to the 10 ergs per square centimeter per second. So it's kind of, according to Fisher, it's the boundary between gentle and explosive evaporation. So conclusion that ARIS data provide very interesting, reveal very interesting dynamics of flow evaporation, and perhaps it's very difficult to fit this into the one-dimensional aerodynamics models. And that here, that's the 5 results that listed again that I mentioned. That first we saw the plasma jet, that with prior the impulsive phase and some activation of energy release around neutral line that we still don't know what it is. And then that another result that I briefly mentioned, that when we look at emission of a carbon line, that you can see a very strong increase in emission, but almost no change in line width. So that we interpreted this as non-thermal emission of carbon. Maybe that some ionization, some non-equilibrium ionization was by particles, or we don't know. And then in the cool lines, in carbon 2 lines, there was almost constant red shift during the whole flare, in the fourth flare. And chromospheric operation was observed in the iron 21 line. It's 50 kilometers per second. And it's generally the special structure could be explained by this general qualitatively by the standard flare model. So that we couldn't define conclusively what the source of this operation is, heat flux or electrons. Thank you.
Okay, so we have time maybe for one question. Yes, please.
Sasha, quick question.
One question. One question.
So, wait, you said you need to make for the recording?
Actually, very, very big. Much more dynamic.
Hi, Sasha. You said there's a six-minute delay from the hot X-ray peak to the iron 21 emission?
Yes, yeah, 400 seconds here.
That seems too very long.
Yeah, very long. Yeah, we really don't know how to explain this. It's probably how to explain that you need some some time to feel that's kind of maybe related to post-flare loops rather than you feel that you have operation in post-flare loops. We have no explanation to this, but it's certainly something.
I just want to say there's some new observation by Hui Tian. He found there's very nice temporal correlation between the iron-21 redshift and the Hartree peak. So the delay of 6 minutes seems to be very long for electron hitting.
Okay, thanks very much. I'm sorry we have to cut the discussion here, but the next talk is just getting set up. And got my notes here. And it's Ying Li, who is also going to talk about chromospheric evaporation in the 2014 March 29th flare observed with IRIS and with ICE.
I'll put it this way so it's not. It's not doing it.
Try just unplug it because it responds to that.
It wasn't. Didn't do that before.
Triggers.
There we go. That was it.
Could you watch the screen down there? I'm telling you that's.
Good morning, everyone. I'm going to talk about chromospheric evaporation in famous X1 flare on March 29th last year, observed with IRIS and Hinata ice. In the following, I will first briefly introduce some backgrounds on chromospheric evaporation and then present observations from IRIS and ice. After that, I will show the main results and finally I give summary. Okay, I had planned to start with the standard solar flare model to understand the big picture of flare. Now I think I can jump to the evaporation process directly. So chromospheric plasma is heated, and due to thermal pressure, it will go up. This process is called chromospheric evaporation. Based on momentum balance, there are also some materials going downward, which is called chromospheric condensation. Once the hot and evaporating plasma cools down, we see the post-flare loops in soft X-ray and EUV passbands. In observations, chromospheric evaporation can be, namely upward mass motions, can be measured as Doppler blue shift in spectral lines. And the downward mass motions condensation can be measured as Doppler redshift in spectral lines. Here shows a summary, an observational summary of Doppler velocity as function as temperature, the formation temperature at different spectral lines from BCS, CDS, and ICE in different solar flares. Here we see the cool lines basically show the redshift and the hot lines show strong blue shift. Based on the observed Doppler velocity at a certain flaring region, chromospheric evaporation can be divided into two types. One is explosive evaporation and the other is gentle. Okay, like the dotted line here, shown here, all the spectral lines show blue shift. It's gentle evaporation. And like the dashed line, the hot lines show blue shift, while the cool lines show red shift. This case considered as explosive evaporation. Actually, these two types of evaporation can converge from each other. Here shows an example: Doppler velocity versus time, and we can say explosive evaporation at an early time, and it converts to gentle evaporation at later time during this flare. In addition, numeric simulations also suggested an existing flux threshold about 10 to the 10th for the explosive evaporation, which means that if the flux is greater than this value, we will see an explosive evaporation. Although chromospheric evaporation has been studied for many years, there still exist some problems, such as discrepancies between observations and models. First, the evaporation models predict that the hot temperature lines greater than 10 K should be entirely or mostly blue shifted. However, the observed light profiles in these high temperature lines show a dominant stationary component, only with a weak blue shifted component. There also gives some explanations, like the stationary plasma is moving perpendicular to the left side, or it's from the top of the flare loop, or the stationary and the blue shifted components are from different loop strands. And maybe the current instrument is not sensitive enough, or the resolution is not high enough to detect the dominant blue shift plasma. Although with these explanations, this problem has not been fully solved. The second problem is high temperature downflows. In the explosive evaporation, there is a reversal from upflows to downflows, and the models predict that the reversal temperature should be less than 1 mK, which has been supported by some observations. However, people also see some higher, like 2 mK or even higher reversal temperatures, which might suggest a rather high energy deposition site. So that's the main problem in chromospheric evaporation. Previous studies mainly used BCS, CDS, and ICE spectral lines in X-ray and EUV wavelengths to study chromospheric evaporation. This present work here is using new IRIS UV spectra and also with ICE to diagnose mass motions in chromospheric evaporation. In particular, we focus on those unresolved problems. Now, IRIS is providing high-resolution slit jaw image and as well as spectra in these FUV and NUV passbands. Let's look at the IRIS observations of the X1 flare we analyzed. This is a slit jaw image, and along the IRIS slit stack line here, we have spectra. And shown here are from 4 different spectral windows. Bottom is a gold soft X-ray light curve. From slit jaw images, we can clearly see the two flare ribbons, and they are separating with each other as time evolves. The spectra also show some obvious features at the flare ribbon. Here shows a snapshot in the flare decay phase. We can see these are the 2 clear flare ribbons in the slit jaw 1400 transition region image. And along the IRIS slit, we can see the bright and broad iron 21 emission 10 Mk plasma, and transition region silicon-4 and carbon-2 resonance lines, also chromospheric magnesium-2 and HK lines. The spectra show some Doppler shifts and light broadening, especially at the flare ribbon. The red box here shows the ICE scanning region overlapping with the IRIS small scanning region. These are the ICE intensity maps in the IN23 for hot plasma and warm IN16 and IN12 lines, or also the chromospheric helium-2 line. Here we can also see the 2 flare ribbons, but with a much lower resolution. In our study, we carefully analyze along this flare region between the 2 short sign lines, and focus on the optically thin lines from IRIS, IN21 and silicon-4, also these 4 ICE lines. Now let's look at the results. Here shows light profiles of iron-21 10K plasma at the flare ribbon pixels in the rise phase and at the flare peak time, respectively. Black lines for observed and colored lines for the multiple Gaussian fitting to separate the iron-21 with the other blended cool and narrow lines. The red curves here for the iron-21 and the vertical line denotes its reference wavelength. Here we also give the measured Doppler blue shift velocity. In the rise phase, it's about 100 kilometers per second, and it can exceed 200 kilometers per second at the flare peak time. Here we see the light profile of iron-21 10K plasma is symmetric and well fitted by the Gaussian shape. Besides, it is entirely blue shifted. So these results, unlike most of the previous results, is consistent with the evaporation models. This is a new result from high resolution IRIS data. We also studied the evolution of chromospheric evaporation during this flare. Here shows the time evolution horizontal axis along the slit of Doppler velocity and non-thermal velocity evolution maps in the iron-21 line and the silicon-4 line. The contours here are the flare ribbon emission from the silicon-4 line. And the vertical line denotes the flare peak time. So from the iron-21 Doppler velocity evolution map, we can clearly see a pair of blue shifted fronts. And these dynamic fronts spatial and coincident with the separating two flare ribbons, the contours. And also this dynamic feature proceeds well into the decay phase, which implies that the evaporation process and magnetic reconnection continue to take place in the flare decay phase in successively formed flaring loops. Actually, this kind of separating pattern seems to be also seen in other evolution maps, like the iron-21 non-thermal evolution map, as well as silicon-4 Doppler velocity, but with redshift mostly, and silicon-4 non-thermal velocity evolution maps. Combining the blue shift in the hot iron-21 line and the redshift in the cool silicon-4 line, we know that this flare shows an explosive evaporation in general. We also further studied the evaporation types using multiple temperature lines from IRIS and ICE. And we selected 3 river locations where evaporation is undergoing. So at the early time at location 1, the red size, we can see all the lines show blue shift as gentle evaporation, and it converts to explosive evaporation at later time at locations 2 and at 3. The cool lines show helium-2. Cool lines show the redshift, and hot lines show the blue shift. Okay, last slide for summary. So using the high resolution observations from IRIS, we detect dominant blue shifts in the high temperature iron-21 line, which is consistent with evaporation predictions. We also found blue shifts co-spatial and coincident with the 2 separating flare ribbons, suggesting that reconnection and evaporation proceeds well into the decay phase of the flare. Also with ICE data, we find in this flare, different locations show different types of evaporation, and there is conversion from gentle to explosive evaporation as the time evolves. Okay, that's all. Thanks for your attention.
Okay, thank you very much, Ying. I can't get out of my seat. So a couple of questions. Yes, please.
So in your second last slide, you show the Doppler shift from measurement of both iris and eyes. Are these measurement points from the same spatial pixel or and at the same time? I think it's really difficult to let iris and eyes observe exactly the same pixel and at the same time.
It means the iris pointing is not?
No, it's not the pointing. I mean, both iris and eyes are doing this raster scan.
Ah, so. Yeah. Okay, here actually we select a region with an area of 4x second and 4x second. So we made some average for the iris data, so co-spatial with the eyes data. Actually, the co-alignment between iris and eyes is about 4x second and 4x second. Since you know the eyes spatial resolution is only 4x second times 1x second, so it's lower than the iris spatial resolution. We made an average.
Okay, you can have one question this time.
You mentioned that an unexpected high temperature dividing line between blue and red shifts about 2 million degrees or above. One possible explanation is if we keep hitting the flare for some tens of seconds, we can reproduce such high temperature dividing line. And one thing in George Fisher's earlier simulation, he only ran the simulation for a few seconds, so it never got that hot for the blue shifts, or for the red shifts. I'm sorry. So well, we can talk later.
Sorry, would you say that again?
So you mentioned early on in your introduction there are two problems. One is blah blah blah. The other is the high temperature between blue shifts and red shifts, like those Millikan results. And one way to reconcile between the simulation and observation is to run the simulation for longer time. So basically, you keep hitting the same plasma for longer time, like tens of seconds, and we can reproduce such high temperature and red shifts.
Red shift?
Yeah, high temperature, like 2 million degree red shifts.
Okay.
Okay, I think this is a discussion that you can maybe have afterwards. We need to move on, but thanks very much again. Okay, so moving on, the next talk is another talk about chromospheric evaporation. I sense a theme here, and it's going to be given by David Graham, and it is about high cadence iris observations of evaporating flare ribbon sources.
Just report again. I mean, it's
You always do that one.
new to Max. Excuse me. See if it takes it. Sometimes it does. Sorry, you want to do it screen. So you use your mirror.
Okay. All right, okay. So again, continuing the theme of evaporation talks here. So I wanted to talk about the 10th of September flare from last year, which Lindsay already very nicely introduced yesterday. So, and most of you probably familiar with these special flares that we have now with IRIS that have been incredibly well observed. And this is just probably one of the best examples of this, because we had incredibly high cadence. It's not been done for a long time, where we had 10-second or better than 10-second cadence sitting on top of the flare ribbon as it evolves. So here the slit position is just in the center of this image, and as the ribbon evolves during the impulsive phase, you find it brightens all the way along the slit here in the center. So the great thing about IRIS now is that we have the magnesium and coronal lines. So we have iron 21, magnesium 2. So this is the kind of top and bottom range of the temperature range of Iris. And we have it simultaneously. So there's no pointing problems with other instruments. And you can have both of these at the same position every 10 seconds, or 9.4. So as we also have been seeing for the past couple of years now that these foot points and these ribbons are very hot. So this is the iron, this is mostly iron 21 in this AIA image. This is the 131 filter. And just that you see the very beginning of the flare, you see the ribbons show up in 131 here, and eventually sort of fill the loops as you kind of expect during the evaporation phase. But just to see these are very hot in the same place as we see the silicon emission. So we know there's some extreme heating going on in these ribbons, and plus we can see the cool response in the chromosphere. So if we look closer at this raster, if we take a small section of this, this is the best thing about this observation. So I'd like to thank whoever was running the planning this day. It's really one of the perfect ones we've got. So not only do you get this cadence across the ribbon every 10 seconds roughly, we also have the fact that the ribbon is moving along the slit during this. So at each pixel along the slit, the ribbon is crossing new undisturbed chromosphere. So essentially you have a chromosphere that's being activated by the ribbon as it passes through it, but you're observing this at this high cadence each time it does this for each single pixel. So for around 80 pixels we found in this section along the ribbon here, you basically have a unique flaring event. So you can look at almost a statistical view of a flare for a change. So it's not just a single foot point, we have this activation going the entire way down the slit of the detector. And just to show here the hard X-ray profiles of this is from Fermi. So we're really looking at this portion of the slit, so we're really looking at the kind of rise phase of the flare here. I think Iris cut off somewhere after about 1750 or something. But we've got the important part here where the energy is really going in. So just to look quickly at the spectra in the Iris detector window, this is a quick look. You see the iron 21 is immediately very blue shifted as the front of this ribbon passes down the slit. So this is just one time here. So see it starts at the edge of the detector basically, and as time goes on, you find the iron 21 emission is starting to decay back towards its rest wavelength here. So I just wanted to show that quickly, just so you can get an overview of what it looks like, just being shifted initially and coming back to rest wavelength. But to do this properly, we really need to fit this gaussines. So I've worked on a method of trying to constrain this, because very early on in the impulsive phase, these chromospheric lines cause a bit of trouble trying to detect the iron 21. So what I've done is tried to do the best job possible, so use constraints from some of the other windows. So there's a lot of silicon 2 in the neighboring window where the iron 12 is. And you can also just use knowledge of line centroids, that they should be in the same place, so they should be shifted equally. And you can do this with the silicon lines from the other window, so you can constrain their width, and you can also constrain their position. And the chromospheric lines, like these silicon lines, and the carbon line as well, have a strong redshifted component too. So we can add that in. So we can really remove every other possibility of what this bump is here to really get out the iron 21. So it's maybe best shown as a movie. It starts to play. So this is just running through a couple of the slit positions. And you see the iron 21 comes, it's almost like a bump under the carpet. So you see very early there's a couple of little bumps to the chromosphere. And here comes this iron 21, sort of moving its way along the window. I'll just show that again, the next one. It's really just to convince you that the fitting is working. I mean, you can see by eye and recognize that this should be the iron 21 line here, even very early on. I mean, so it just comes along like this. So it's really incentive maybe to be extending this flare window here, because the edge of the window is about 350 kilometers per second shift. If we were to have it a bit brighter, then we could see, maybe find the shifts earlier on, especially where the emission is low and it's difficult to detect. just to be quick here, the subordinate line, you can take a bisector of it. So it's just an approximation of how much it's shifted. So really it's only looking at a sort of upper limit to the shifts. So this is the subordinate line. We use this since it's not as saturated as the resonance lines. This is also the 2791 line, which is on the blue wing of the resonance lines. This also helps because there won't be any redshifted component from the resonance line interfering with this. Really, to show it all in one slide, so this is the iron 21 flows and the magnesium intensity. You can see the black and white image is the intensity in the background. The magnesium flows are co-spatial with the intensity. Interestingly, the iron 21 flows always seem to have a delay, mostly have a delay in time. In a few places it's maybe only a couple of time steps. But really we're having, either there is a real delay here, or we're having trouble detecting it at its very earliest instance. And the emission may be very weak where this flow actually begins. The difficulty is that we don't know entirely if these are co-spatial. I mean, geometry effects here, you're now looking at this new problem with iris almost. You have resolution that's so good that now you need to worry about the inclination of loops and things. I mean, before this would be a pixel in ice or something like this. So this is a new problem, really. So you don't know whether this delay is true. These are co-spatial. So we really need to look at the AIA data. As I was saying, this means we have 81 flares almost for the price of one. So you can take the beginning, you can take the earliest detectable iron 21 emission, we can line them all up at the same time step. And you can see this beautiful sort of correlation between every one of these pixels. They all show more or less the same decay of flows, which are much longer than we sort of anticipated. Seems to be about on the order of 500 seconds. A couple of them towards the north are slightly, it's almost like they're offset. Like we're maybe not detecting the earliest emission here. But the majority, maybe 60 out of the 80, lie on this curve here. In the chromosphere too, we've been able to see this down to, so now we're looking at decay times in the chromosphere of about 60 seconds for the condensation flows to stop. Now this is much faster than what was observed before, back in the 80s. But we think it's due to better spatial resolution than the temporal resolution, where before these things were spread out. So you'd have subsequent things happening, and you would sort of spread this decay out. But on the other hand, it's quite close to what the early Fisher theoretical simulations showed, of decay about 60 seconds. So the last thing I wanted to show is to answer Joel's question yesterday. But, yeah, we can use this great observation to really think about the characteristics of the ribbon. And for your simulations where you want a flux for your input energy, you need the size of the ribbon. So here what I've done is track the spatial profile of the ribbon along the slit, and taken an average of each position, and taken an average in time of each position, and also the average time profile of them as well, which is the black curve here, and you have the green curve, the spatial curve. And you get a full width half max of about 30 seconds. So these ribbons are only really dwelling in the chromosphere for on the order of about 30 seconds. So it's much faster than some of these simulations that we've been running have shown. And also we have an upper limit to the spatial scale here, because it's combined with, you have the point spread function of the detector, also the fact that the ribbon's inclined to the slit, and it's also moving along the slit as you measure this. So we reckon in this portion of the slit, where it's moving at a quite constant speed, it moves about 0.025 arc seconds per second. So whatever that means in terms of geometry of the region or the magnetic canopies and things above it. So really that's pretty much all I wanted to show. There's a lot of detail in there that you can maybe ask later in the week, especially about the fitting and some of the lines. But really just this was the one thing we sort of got from this, is that it does seem to be a progression of individual events here. So the entire flare, hard X-ray curve and soft X-ray curve is really kind of superposition of all these sort of individual parts of the chromosphere being lit up. So really when you want to think about modeling, you want to sort of think about how is it really right to be modeling an entire Arc X-ray spectrum when these are always quite small and quite rapid activations of the chromosphere? We're also finding the condensation times are close to the simulation, but we're not so sure about the iron 21 decays, why they take so long to decay back to the rest wavelength. If we're still looking in the foot point region, so what does this really say about the dynamics here? And also we can, like I said, use these parameters for modeling. So that's all I'd like to say. Thanks.
Okay, thanks, David. Is there any questions? Marcus, yes, please.
When you look at upflows at one single location, how long does it last? Just at one pixel, because that will give us an idea how long the heating, lasts for one elementary burst.
So the upflow is, so this is a kind of superposition of all of the pixels. So one upflow is lasting sort of on the order of 500 seconds. If that's what your question was. Yes.
So at every foot point, you have about 500 seconds.
Yeah, before this flow goes back to 0 kilometers a second.
Okay, Nariaki, yes?
That plot, the left plot,
Yeah.
some of the slits may cross non-flare ribbon areas.
Every one of these is a position where the ribbon has activated the chromosphere. So all of these pixels.
So just the ribbon areas.
Just the ribbon areas, yeah.
But there is some data for non-ribbon areas, right?
Yes, yeah, there is.
And maybe some areas have dimming signatures. This is a highly eruptive event. So I wonder if there is some dimming signatures.
The problem is that the where it's not a flaring portion, it's very difficult to observe the iron-21. So there's hardly any intensity anywhere else, unfortunately.
Okay, okay, maybe one more quick question. You had one already, so I'll give one to Jean-Pierre. If it's quick, please.
Yeah, just a quick comment about the dimming. You see dimming mostly in the EUV. In iris, you don't see as much dimming because there's no free bound absorption there.
Okay, I'm sorry to have to wrap up the discussion, but we need to move on, so thanks again, David. Okay. So the next talk is by yet another Scottish person. This is by Graham Kerr, and he's going to be talking about the magnesium-2 H and K line emission observed during a solar flare. And I believe the solar flare is 2014, March 29th. No, it's not. It's not. Okay, it's another one.
Maybe.
Oh, sorry.
Yes. Yes.
Yeah, so I'm Graham Kerr. I'm a graduate student at Glasgow working with Lindsay. And we have been looking into the magnesium-2 emission from IRIS in an effort to understand some chromospheric diagnostics. And so I won't go into too much of a background of flares because Lindsay did a really good job of that yesterday. And also the magnesium will be talked about a lot this week in a lot more detail than I could give here. So I'll only say briefly, we're interested in this because it's a very strong chromospheric line. So the bulk of the radiative output from a flare is from the chromosphere. So it's essential that we can build up diagnostics of chromospheric emissions. And one of the strongest lines from IRIS is this magnesium emission. So it's an optically thick resonance line. That means it forms in multiple layers of the atmosphere. And it has this kind of complex structure in the quiet sun that is made up of these components. So it ranges from the upper photosphere to upper chromosphere. And it's been previously studied by balloon-borne experiments, Skylab and OSO8, mainly in the quiet sun and network and Plage. But there's only been one flare observation, and that was Lemaire in 1984. And so we don't really have a strong understanding of what this line does during flares until now that we have IRIS. With IRIS, we can get routine observations of flares, including this line. And so in order to understand what's going on, we did an observational study of a flare that occurred last year, and we also are starting some modeling using the Radin code that we learned about yesterday. So we selected a flare from 2014 in February. It's an M1.8 class event, And we chose this one because at the time it was one of the few flares in Iris that had really nice coverage along the slit, along the ribbon, sorry, but also had good rescue observations. And we used the rescue observations to drive the radiation hydrodynamic models. A couple of things to point out about this is this was accompanied by a failed filament eruption in the southeast of the field of view here. So we focus on this northern ribbon because down here the field of view becomes very complex and it's kind of hard to separate the ribbon and the filament spectra. So we focus up here. And also from the rescue spectra, we had very few high energy counts. So if we did some imaging of this, the non-thermal sources weren't really associated with the ribbon structure, but some thermal sources were. So this is 6 to 9 keV, and you had these really nice thermal compact sources. So it seems to be a very thermal event. Also, I should say, this is an 8-step raster program, setting 2 arc seconds per exposure. This gave us a repeat cadence in each position of about 43 seconds. So before I go into more of a quantitative look about this flare, I thought I'd just give a good general overview of how the magnesium lines change during the event. So this green line is this quiet sun profile I showed in the first slide. And this red line is from the flaring region. It's a pre-flare. So this is a few minutes before the peak. And this blue line is the same pixel at the peak of the flare. And you see that even in the pre-flare, this central reversal feature that's ubiquitous in the quiet sun is no longer present. If it is sometimes present, but it will disappear and reappear in very short time scales. During the peak of the flare, the line intensity increases, you get a significant line broadening. The line centroid appears redshifted. And you also, in some of the profiles we looked at, you got a blue-wing asymmetry. And the central reversal feature during the peak of the flare was completely absent. And as Dave was just saying, these subordinate lines go into emission during the event. And if we look at the light curves of this, so these are light curves of the K line, the H line, and the 2 subordinate lines. And they have a very similar temporal profile. They have a kind of gradual ramp up of between 90 and 200 odd seconds before you get to the peak. And then there's a very quick decline followed by more gradual decay. And this is one frame, so about 42 seconds to decay back down here. That's about 20 minutes to decay fully. And if we show the maps of these integration intensity, so it's not showing up fantastically well here, but you can see there's quite a lot of small scale structure you can get from Iris. So you see intensity variations of very small scales of less than half an arc second. I'd also like to point out the highest intensity emission is towards the edge of this ribbon structure at every point, so it kind of curves up northwards and down to the west. And the most intense emission is in the vicinity of these resty thermal sources. And so because we had profiles without a central reversal, we thought, okay, have these become optically thin during some process during the flare? And that would obviously guide our analysis techniques. And so we investigated the K to H intensity ratio. And this is a measure of the optical depth during the flare. In the optically thin case, this would be a ratio of 2. And this has been seen in off-limb measurements where the central reversal is filled in, you get this sort of ratio. During the flare, however, we keep a kind of constant value of about 1.15 on average. And so this means that the flare is still optically thick, despite lack of a central reversal. So there's something causing this, the source function to increase rather than decrease, which could be related to the density. And there's no large-scale increase or decrease in this ratio, but you'll see that around the peak of the flare, in the strongest flaring sources, this dispersion decreases. And this is still something we're working on to try to understand. So right about the peak, the spread in these K/H ratios becomes less. These are cuts along the y-axis. So because we have optically thick lines, we didn't want to fit Gaussians, so we took a non-parametric approach to investigate the quartiles. So we split the line up into 4 equal areas by computing the normalized cumulative distribution functions. And from them, we can grab out the wavelengths that correspond to the 25, 50, and 75 percentiles and compute these measures and see how these measures vary with time during the flare. So we have the line centroid, from which we can get Doppler motions. We have the interquartile range, which gives us a measure of the width of the line. And we have this measure of skewness or asymmetry, which looks at the spacing between the red wing and the blue wing relative to the line centroid, and we normalize that with interquartile range. So looking at the velocity first, we see downflows of about 15 to 25 kilometers per second. And so this dotted line is an intensity light curve from one pixel. And these are velocity curves. You see very nice temporal matching between the peaks in velocity, peaks in light curves. You also see reciprocal bumps here. So you see every time there's a bump in light curve, you see a bump in velocity. The difference here is that the light curves take about 20 minutes to decay to the background, whereas velocity takes 3 to 5 minutes to come right back. Also, I should say this kind of cuts off, so I haven't shown the full decay here. But the velocities take about 3 to 5 minutes to come right back down again. And also here in the spatial association, we see these contours are intensity. The velocities are confined to the outer edge of this ribbon structure, and they die away very quickly. So these really seem to be associated with the initial energy input to the atmosphere. Looking at the widths, we see a significant increase in the width of the line, going from about 0.27 arc seconds to about 0.5. The K line is slightly wider than the H line on average. So this increase in the width could be from unresolved flows or an increase in scattering to the wings, but it also could just be because we're seeing enhancements at multiple layers in the atmosphere, so we just get a broader line. But I think we really need the numerical modeling to understand this observation. The final measure was asymmetries, and so for these 3 panels here, we see a reasonably strong blue asymmetry. This is the peak of the flare, but they're only associated with the strongest flaring sources. So although we have an overall redshift in the line, so downflows, we do have a blue asymmetry. So there's some complex motions going on in this event. So this is a stronger blue wing compared to the red wing. And as I was saying, we've started some modeling of these lines using the Radin code we learned about yesterday. We're running a small parameter survey to investigate what magnesium does with this, with the code. But because Radin uses complete redistribution to model magnesium, we're going to take the macroscopic outputs of Radin and feed that into a modified version of RH, which can give us more physically realistic magnesium profiles. So we can put in time-dependent slices of the Radin output into RH to understand what's going on. And just briefly, I want to comment on this second event that we're starting to look at. So we are looking at a very thermal event in February, but we want to see what's the difference between a thermal event and a very non-thermal event. So I found an X-class flare that has very nice iris observations. So it's got 4 subpositions going across the ribbons. And as well as investigating the magnesium 2H and K resonance lines, we also look at the wing emission and look at continua. So following Klein and Heinzel's approach to get the NUV enhancements, we can find continuum enhancements from iris observations in the chromosphere. And we've also got Hinode SOT red, green, and blue continua emissions, which means we can get some white light observations and tie together the white light and the NUV continua from this. And so that'll give us a better idea of the chromosphere using iris. And so just to summarize briefly, I'll leave these up here to comment on, but there's some outstanding questions. So what's the difference between or is there any difference between the magnesium 2 profiles between events? Why are the lines broadened so much? And what do the model outputs tell us of the potential diagnostics in these flares? And are there any potential diagnostics from these subordinate lines? And I believe there are some on the way. So thank you very much.
Thanks very much, Liam. Time for some questions. Bart.
You said there was a velocity difference between the K and H lines?
Yeah, so it's so the K line was a little bit higher, but so maybe it's not easy to tell in this plot. Each of these lines these are 3 cuts along the y-axis, and each of these has a K line and an H line. So the K line is always consistently higher, slightly, but the errors on this are within that range. So it's kind of hard to tell from this observation.
So is it a few kilometers or less?
Probably less. It's probably about 1 kilometer per second.
Okay, Jean-Claude?
Yes. How do you derive? You have a non-reversed profile.
Yes.
You derive the velocity from the the shift of the centroid.
Yes, sorry, should have said that.
Did you look at the wings, the shifts in the wings of the line?
No, it's line centroid only. So we took the rest wavelength from the quiet sun spectre with the reversal to get line centroid, and then we used this this measure, which gets the light centroid position to measure the velocities.
And what is the typical intensity enhancement at the peak of the flare?
In terms of percentage, or I don't know percentages, but it's quite significant. So it goes from, so this is the pre-flare, this is the flare. So it's 2 or 3 times at least.
Okay, any further questions? Okay, if not, then thanks very much again, Graham. Okay, so our next talk is by Wenjian Liu, and she's also talking about the magnesium 2 lines, and this is the one about the March 29th flare.
Good morning.
Please watch the clock down there, okay? Okay, so thanks very much. Take it away, Wenjuan.
I'm also talking about the magnesium lens. It's on the famous flare. So, as Fletcher said yesterday, and also Graham said, the magnesium lens has strong chromospheric emission during flares, and there are not many observations and modeling before. So we are studying the magnesium 2 lens. This slide shows the light curves of the flare in soft X-ray, hard X-ray, also from the iris slit jaw images in 1400 and in magnesium. The iris has 8-step rasters with the raster cadence of 75 seconds. And as we see before, in stock, this is slit jaw images in 1400. And here shows the spectra at this time at one slit, the slit number 4. And from the spectra, we can see the greater enhancement in magnesium to H and K lens, and also superordinate lens. And we can also see the red asymmetries at this time. To calibrate the iris spectra, we compare the spectra with the Rossby observations. The red one is from iris spectra in the quiet sense, and the black one is from Rossby observations. And we can see in the wings of magnesium lens, the intensity from iris is comparable with Rossby. And during the flare, we here plot the spectra in 1 pixel at slit number 4. We can, on the black colors, is the spectra in the quiet sun. For comparison, we can see the enhancement of the intensities from in the flare. And we also see the subordinate lens, and some iron lens also goes from absorption to emission in the flares. The lunar panel shows the spectra after the peak, we can see there is a great red asymmetry at this time. To compare with the observations of Lamar, they also see the enhancement of emissions in HK lines and this subordinate lines. To study the flare in all 8 slates, here shows the intensity of the magnesium 2H lines in all slates. We can see that the intensity increases at this time, and we can also see the movement of the ribbons when the intensity increases at different times. Here the K to H ratio as the flare, same as the flare with Lamar et al. Also as the flare with Graham, we found for this flare the K to H ratio is about 1.1 with the sigma at 0.019. And for the subordinate lines, we see the intensity increases at this time, and we also see the moves of the ribbons to the south, and the same as the previous observations by Lamar et al. For the asymmetry of the red-blue shift of the magnesium 2 lines, we plot the center of gravity of the magnesium 2H lines, and we can see there are a greater blue shift before the flare, which is due to the eruption of a filament, and at the flare peak and after the flare peak, there are red asymmetries in the magnesium H lines. Here shows the center to peak ratio of the magnesium H lines, which shows how the line profile is reversed, and we can see in the flare footpoints, the center to peak ratio is very large, which is close to 1. And for the line width, we plot the 4 widths at half maximum of magnesium H line. For the line profile with a larger center to peak ratio, which is less reversed, and we can see at the peak time and also after peak, the FWHM is very large, which is close to 2 angstroms, compared with the FWHM for the quiet sun, which is about 0.5 angstroms. And here we compare the magnesium K spectra from observations in 1 pixel with the synthetic spectra from the famous flare F2 models. The colors lines are spectra at different time, and the black lines as synthetic spectra with different turbulence velocity. We can see that the synthetic central line intensities are comparable with the observations at this time, but the synthetic intensities in the winds are lower than the observations at 1646, but comparable with the intensity at later times. It also shows that the synthetic line profile are broadened by the microturbulence in the line core. And to see how the parameters of the atmosphere will affect the line profile of the magnesium lines, we use the static flare models from Riccia and Canfield. Here shows the effect of varying the spectral index delta for the electron beams. And we can see that electron beams with a lower spectral index will enhance the line intensities in the vanes. The next slide shows the effect of varying energy flux of the electron beams. As expected, the electron beam with a larger energy effects will give a stronger magnesium emissions. And this one shows the effect of varying the on the coronal pressure. And we can see the stronger the coronal pressure, the stronger the emission in magnesium lines. For summary, here are summaries of observations. I will not read it. And oh, sorry, my computer. It's not finished.
So when you put up your conclusions and you finished your talk now?
I will finish it. The other summary is a summary about the model, but I don't know, it crashed.
Okay, well, I think in that case, since we saw your conclusion slide, maybe we should stop the talk now and allow people to ask some questions.
Okay.
So can we thank Wenjuan, please, for her presentation? Okay. So what happened? Did it crash?
I don't know.
Oh, there it is. Okay, we'll put the summary up then, that's fine. And maybe we can just take some questions while the summary is there. Does anyone have questions? Yes, over there, Tom.
You presented some very nice results, both from an observational point of view and then referring back to some of the theoretical work that was done in the past. And I think the key here is to remember that the magnesium lines are very, very optically thick. They are the dominant cooling source, or one of the dominant cooling sources in the chromospheric plasma, but also they retain an imprint of the photosphere quite strongly in the very broad wings of the lines. And so when you talk about broadening in these lines, it's very important to understand that it's not velocity broadening that's going on by and large, but really another process called radiation damping. And you showed that quite clearly in the Pandora calculations that showed that when you change the turbulent velocity in the atmosphere, only the very core of the line is affected, and the wings are not. And what those wings are telling you is that the excitation, the heating of the atmosphere is going on very, very deep. And the consequence of that is that a lot of the cooling that's occurring in the flare is happening in places that we're not seeing with iris or in the X-rays. It's probably happening in the H- continuum, for example. So I think these are absolutely spectacular observations. I think it's terrific that the iris people had the foresight to include this important chromospheric set of lines. And thanks for your talk. It was very nice.
Thank you.
Okay, so let's just have a couple of quick questions. I think I'm going to ask Hugh first and then Peter, and that's it.
Maybe Peter could also answer. I just wanted to know if the F2 model has too low a pressure, really. Do we favor a higher pressure?
Can you answer that, Wenjuan? Do you need high pressure?
Yeah, I think Peter can answer.
I just want to comment on these two comments, yes. So the first one, I am not sure if these broad wings are really formed in the photosphere because the line is extremely optically thick, and I think that these broad wings, which are of course not affected by microturbulence as you have seen, I think they are formed in the flaring chromosphere because chromosphere itself is optically very thick. So this is one comment. And you ask about the pressure of this F2 model. You know, F2 model is of course model which was designed by Machado, Jean Everett, and others. It's rather old stuff, but we consider it as an example of temperature structure, yes, and some coronal pressure, nothing more. And coronal pressure is rather high. It is of the order of 10 to 2, less than 100, yeah.
So should it be more than 1,000? Is there anything about the Iris observations that was pointing to a higher, or static model, a higher pressure?
But as you have seen from these simulations which we performed from Ricciasi field models, if you increase the coronal pressure up to 100 or 1,000 dynes per square centimeter, you get the line profiles which are not very much reversed. And this is observed by Iris.
Okay. Thanks very much. We'll need to stop the discussion here, but we may have the opportunity to return to it. The next talk is Fatima, who's also talking about this flare and about her observations and modelling related to it. Fatima, can I ask you to watch the clock down there? You see on... Yeah, okay.
Yeah, so good morning, everyone. I will again speak about the 29th merge flare. In this case, I will show some relative hydrodynamic simulations in order to study the chromospheric emission. So this is the outline I'm going to follow. I will briefly introduce the flare, which I think is not necessary anymore, so I will go fast on that part. I will show the RESI observations and how can we, from the RESI spectra, estimate the parameters of the non-thermal electrons, which are going to be given as an input for the radiative hydrodynamic code reading. And with that, we will be able to study the continuum emission and the line profiles in several wavelengths. I will briefly speak about some further steps, some further work, and we'll conclude with some final conclusions. So this flare was classified according to GOSO as an X1 class flare, and as it has been pointed out previously, it has been observed by several instruments, and one of them has been RESI, which covered the whole impulsive phase of the flares, and this is very nice. So it has been also observed by several other instruments, as SDO, IRIS, RESI, HINODE, and the Dan Solar Telescope observed it in G-band and with IBIS. So we have H-alpha and calcium observations, calcium 2. So quickly, I will move to the RESI observation. So here we have the light curve, and we can see that there is, this is at 100 kiloelectron volts, and there is a very strong peak in the impulsive phase of the flare. All these dashed lines are actually the time intervals at which I got the spectra, and at each spectra, here we have an example, at 1746, between 1746.14 and 1746.30, we feed the spectra to a thermal component plus a thick target component, and from the non-thermal component, we estimated the power law index, the cutoff energy, and the power of the non-thermal electrons. And once we have the power of the non-thermal electrons, we can estimate the area of the foot points, and dividing the power by the area of the foot point, we can get the flux of the non-thermal electrons. So actually, the selection of the foot points area is a critical point for the estimation of the flux of the electrons. What we did here, so this is iris slit jaw, and we selected the foot points of the flare as the threshold in the iris image of 9700 counts. I plot here the Resic contours in between 30 and 70 kiloelectron volts. This is actually the slit, and you can see that there are some time intervals, some snapshots at which both contours overlay and the slit overlays over the X-ray emission. So I will actually compare observation with simulation at these certain times. So taking into account the area of the foot points, here we have how the parameters change in time for the non-thermal electrons. This is the power law, the spectral index, the cutoff energy, the power, and dividing the power by the area, this is the flux of the electrons. So taking all these 1, 2, 3 parameters into the code, we get into the Radin code, we get the hydrodynamic response here of the atmosphere. The dashed line is the initial atmosphere, so the pre-flare atmosphere. So far we have, this is an ongoing project, so far we have only 23 seconds from the beginning of the impulsive phase of the flare. And so we have here several things happening. The temperature increases, especially in the corona due to the electron hitting rate. You can see in this case the boundary condition is a reflection, as Joel was mentioning yesterday. That was one of the possible scenarios. So you can see at some point reaches the upper corona and then comes back, and is when actually, because you have stronger heat in the corona, temperatures increases. This is the electron density. You can see quickly increases in the transition region as well, and this is actually the velocity profile. At different times you have strong velocity going, so in our case positive velocities are flow and negative velocities are downflow velocities. So you have strong velocities going upwards, reaching up to 700 kilometers per second, and some negative velocities in the chromosphere going down flows. So focusing on the velocities, comparing the upflow velocity with the sound speed, we can see that even after 3 seconds we already have supersonic velocity. So we have really shock waves moving to upper layers. And focusing on the chromosphere, downflow velocity, this is the minimum velocity along the whole loop. And you can see you get the velocities of the order of 25 kilometers per second within the first 15 seconds. So that actually, it has, for this specific flare, it has been pointed out that there have been some soundquakes, and actually these negative downflows, as reported by Kosovichev early in this session, that can be an explanation for the soundquake observation. So it's something that we should look into. Moving now to some evaporation flows, it has been previously shown. This is a slide I got from Peter Young, but previously there have been some observations about this flare. I just wanted to mention that there have been some explosive evaporation. So you have some plasma moving down flows below. Here, I think you pointed, where are you? I think you pointed out it was about 1 megakelvin. I got from this slide that it was about 4 megakelvins, and you have some plasma evaporating only at temperatures above 10 megakelvin. So comparing these results with the ones we get from the Radin code, at this time, the 1745-33, which is actually about 1 minute earlier than the observations, we get that we have downflows for temperatures below about 1 megakelvin and upflows for temperatures above. So roughly is something that we can say it's comparable with observations, but as I mentioned, we have to keep going on the simulation for another minute, and we are expecting to reach higher temperatures in later times. So moving now to the line profiles, I will show here some synthetic lines. In this case, we have H-alpha and calcium lines, calcium 28542. These two lines are resulted from the Radin code, while these two lines, magnesium 2H and K and oxygen, have been obtained using the RH code and the atmosphere from the Radin code, so as a snapshot in every time step. So there are actually some, as I mentioned before, some observations in H-alpha and calcium from IBIS, and so we could, I haven't done it so far, but the next step will be compare observations with simulations. And we have from IBIS, magnesium and oxygen lines. So I will focus in this case in the magnesium line. I will compare that one with the observations. But before that, I will show how the light curve shows. So what we did is to integrate the intensity along the line profile. And this is how the light curve changes. And it surprised me, first of all, for example, oxygen, you can see at very initial times, it decreases and then it increases again, which is different behavior than for the rest of the three lines I'm showing here. Well, for example, for the magnesium line, you can see at later times you have suddenly an increase of the intensity. We have to look in more detail into this, but I will say this is because of the plasma. I don't know. There was some in the variation of the atmosphere. At later times, you can see that there is some plasma moving downwards. Here, you can see this is stronger. And you can see also there is kind of secondary emission peak here in the temperature. This is because the atmosphere is already ionized. So all this in the chromosphere may explain the emission in the magnesium line, which is formed in the chromosphere. But it's something we have to look in more detail. So moving to the observations, what we did here is to get this pixel here. And this is how the magnesium line looks from the observations, and comparing the lab profiles with the simulations for these very few seconds at which the slit coincides with the X-ray emission. We found, first of all, narrower profiles, and second, stronger. We divided the synthetic intensity by 20, so we have found stronger intensities and narrower profiles. It's something we have to study in more detail. Moving to the continuum emission, it has been pointed out by, there is this paper in which they observed that the continuum increases, especially around 20 in the ultraviolet, between 100 and 200%. So comparing these results with the observations, for the first 25 seconds, we can see that it increases, and it increases about these orders of magnitude at all these ultraviolet, visible, and infrared. We are expecting to get a stronger or a higher enhancement of the continuum at later times. So, and moving on to further work, there has been two disciplines so far. There is the hydrodynamic observations in one side and the particle study using the Fokker-Planck equation on the other side. So what we want to do is to couple all these two effects and apply them to this flare. And the way it will have been done will be to, so from the stochastic acceleration, we get the collisional heating rate, which is actually given to the Radin code, updated in every certain time step. The Radin code will calculate the whole atmosphere and will give the density distribution to the flare code every time step. So as a summary, so we use ratio spectra to estimate the variation of the electrons. This actually can be improved by fitting the spectra and applying a forward fitting procedure, so we will not need to assume any power law. Using the high-resolution spectroscopic observations from IRIS, we could compare simulated lines with observed ones at several wavelengths. And in the case of magnesium, we present our lines present our profiles than the observations. Previously, I think Peter was mentioning that it cannot be due to turbulence. We have to look into it. Continuing emissions is an increase, and we expect to reach observed increases at later times. IRIS provides a good opportunity to study the chromospheric emission and test the energy deposition of the solar chromosphere. And as a step forward, we want to combine the Fokker-Planck equation with the Radin code.
Okay, so time for a couple of questions. Yes, Jorrit.
Could you go into a little bit more detail about how you model the magnesium to HNK emission in RH?
So
I have been a little bit involved in how we do it here, and it was never ever designed to do flares. So you might want to look at your assumptions that go in there and see if you're actually doing it properly, because that might explain some of the differences in the light and maybe even in the light intensity.
What I have done so far is to get the atmosphere at every certain, in this case every second, sorry. Temperature, density, and all the properties of the atmosphere. I gave that to the RH code. I assumed partial redistribution and included as background all the other elements. So I mean, it's something most probably. I'm not an expert with the RH code, so I would like, if you have been working on this, I would like to show you what I have done so far and how.
Okay, David.
This Radin simulation of H-alpha line shows that at the initial stage, there are there is red asymmetry at the initial stage of the flare onset, and after that there is blue asymmetry. I mean, the peak of blue wing is higher compared to peak of red wing.
So I would say at initial times you have this initial peak here. Let's use the peak, but then you have some velocities moving downwards, and I would say this is actually the explanation of this secondary peak here.
Yeah. I have posted here, and our observations shows exactly the same behavior of H-alpha line profile evolution. So there are red asymmetry at the initial stage, and after that the asymmetry is reversed into the blue.
So these are observations?
It's a crisp SST observation of H-alpha line.
Oh, that's interesting.
Thank you.
Okay, so I saw Jean-Claude at the back there. Maybe you just have to shout.
Yes. I have a question concerning the HNK modeling. And this is a question actually that I addressed to all modelers in the audience concerning HNK. Do you take into account the pumping process from the fundamental level to the 5D level by the Lyman beta line, which of course will be much increased, and it has been shown by Lemaire and Mutobros in 1983 that it was important in the modeling of flares, so it should be important in the modeling of flares also, I presume.
Yeah, you're right. I have not taken into account that. We don't exactly know what's happening with flares because it's hard to, I mean, quiet sun plage, they're having several observations. Flares, there are many things, have physics happening. It's hard to separate what's happening around. I agree with you, most probably is an important effect to consider, but in this case we have truncated the Lyman beta. profile. So
I see a sea of hands, but I'm also aware that it's now coffee time and people want their coffee. So I'm afraid I'm going, let them discuss a bit. Bart says discuss a bit. Okay, we'll let them discuss a bit. In that case, I think maybe, Hugh. Hugh's been waiting patiently.
I like the RESI analysis, but I think it's dangerous to push it to the area measurement. I think that's very risky, and it should be treated as an upper limit. Perhaps you should try models with maybe 10 times the beam intensity as a guide to what might be happening, but we really don't know what the areas are.
yeah, and you have also an uncertainty on the cutoff energy as well. So yeah.
Okay, I think we'll go for Jorrit and then Peter.
I just wanted to react to the question from the back of the audience about the pumping by line of beta. We have tested this for the Bifrost models, which are clearly non-flares. And for those models, it is not relevant, but there's no reason why it cannot be included. So it turns out to be relevant. It can all be considered.
Oh, that's good to know.
Okay, thank you. And then Peter.
I include in my code. I first compute the fraction for hydrogen, I get like line, and then I include it in magnesium calculation to ionize it. So it is included, but I didn't test it how that is important in fact, but it is included for level.
You include the actual value of the line.
Yeah, but it's there.
Interesting to note as well that with Eve, for some flares, we can, of course, measure the Lyman beta intensity enhancement during flares. In MEGS B, we have Eve Lyman beta averaged over the flare.
Lyman beta is always in strong emission like Lyman alpha in flares. But the question is how much this affects the magnesium ionization of depth of the flares.
Okay, any other questions about magnesium 2? No, no, go ahead. I cut you off before, please.
Just for clarification for Hugh's question, we Christina used the IRIS feature image point area quadrant.
Okay, I sense people thinking coffee. So, oh no, wait a minute. Sorry, look, there's Adrian Daw. Is it a local announcement? Coffee and e-posters. But first of all, before you all go, could I ask you all to thank our speakers this morning again? And what time are we back here, Bart? 11:15. 11:15. Okay, so thank you. Sorry.
We're leaving flares behind us and moving to chromospheric dynamics. And we start with a review by Luc Ruppe van der Voort, who will talk about chromospheric and transition region dynamics.
Not my problem. I was speaking loudly. So, Luc.
Yep. Okay, I'm going to start out by putting the focus on the quiet sun. This is a quiet sun region close to the center of the disk. You see the network, the bright points of regions with strong magnetic field. So we have the strong fields of the network along this ring, and we have a quiet region in the upper left corner. If we now look in the core of one of the strong chromospheric lines, like the calcium 8542 line, you see quite a difference between the internetwork and the regions around the network. So the internetwork is dominated by shock waves, while the regions around the strong magnetic fields, we see the fibrils and we see spicules. This is also clear from the spectral evolution. So if we look at the point here, we see the spectrum as a function of time. And here you see clearly the effect of the shock waves. You see the strong shifts towards the blue, and then a gradual decay towards the red. And sometimes you get this emission peak in the core of the line. And these are the bright grains that you find all over the place here. But if you then compare to this region or this spot here, you see that the line profile changes on a much shorter time scale. And it also changes very quickly from red to blue. And not only in time, but also in space. So this is an effect of the of the spicules. So spicules you can of course observe much easier at the limb, and we know from all the observations that the spicules are heated to temperatures beyond the chromosphere. But now with iris, this can be shown very nicely. So in the movie that you see here, you see a transition region signal of the silicon 4 line that is in blue, and it is on top of the magnesium K spicules that you see in red. So they ride on top of the magnesium spicules. Now we have looked in more detail at the number of spicules that we have traced one by one, or that we could follow in time. And we do this from a combined observation with the calcium 8 and iris and ANA. We see the spicules in all the channels, and we can of the 54 spicules that we could trace throughout the lifetime, we see that more than three-quarters of them, they fade in calcium 8. And for many of them, when they fade, we see that they brighten up in silicon 4. So we interpret this as a sign of heating. So when the cold plasma that we observe in calcium 8, when that gets heated, then it fades out of the passband, and then it gets brighter in the silicon 4 line. Here we look at one spicule in more detail. We see the movie on top in calcium 8 and magnesium and silicon 4. And we trace the spicule with the slit, and we plot the maximum in intensity along the slit as a function of time. And we also follow the spicule with the slit. And we can do this because we can always observe the full lifetime of the spicule in magnesium. And then we can follow the spicule, and we can also see the fainter signal that we can observe in calcium 8 after it fades away. So it is also important to point out that when the spicule fades in calcium 8, it typically fades along the whole spicule and then gets brighter along the whole spicule in silicon 4. So it's not only heating along the top, but it's heating along the full length of the spicule. But apart from that, we still see that a significant part of the spicules get brighter at the top in silicon 4. We can observe these spicules also on the disk, and this can be done in the wings of, for example, H-alpha. So here you see a movie at the center of the disk. In the far wing at 54 kilometers per second in the blue wing. And then we see these dark absorption features that shoot out from the strong fields. And we studied these dark features in detail, and they behave in the same way as the spicules that we see on the limb. So we call them rapid blue shifted excursions. That's because they show an asymmetry towards the blue for a short duration. So you see the absorption feature here, and the spicule or the spectrum is shown at the cross here, and you see this asymmetry towards the blue that lives for a short time. We not only see these excursions towards the blue part of the spectral line, we also see them towards the red. This is an observation at the center of the disk. So we look down on these features. And now the blue shifted events, so the asymmetries towards the blue, they show up as white features. So you see all the white features that shoot out from the region down here. But we also observe these darker features, which are now the asymmetries towards the red. And now I'm not referring to the ones that you see down here and down here, which are clearly a downfall event, but I'm more talking about the features that you see, for example, here. So you see the dark features that behave in the same way as the white ones. And it's also shown, we interpret this as an effect of three kinds of motion that are important for the dynamics of spicules. So we see upflows, and we see a swaying motion, which is very clear when we observe spicules towards the limb. And we also see the effect of torsion or rotation. And this is also shown in the figures here. You see the spicules in the calcium red wing. And when we then look at the spectrum along this line, we see that the spectral signal changes very quickly from blue to red and the other way around. And this is also shown in the Doppler map in the bottom. So you see both white and dark very close together. And you might say, okay, this is just an effect of a chance alignment. But we also refer to the features that you see here, where you clearly see the group behavior of both black and white features. And we see sometimes how they change from one side to the other. So basically we see a blue shift that changes to a red shift. And this we can explain with the combination of these three kinds of motions. So when we look at the iris data, we can see a clear association of these spicules on the disk and the bright jets or the network jets that shoot out from the network. And there's one very nice example down here, where you first see an RBE, a very big one, that is associated with this bright jet down there. When we compare this with the Doppler movie, we can also see, for example, in this region here, how both redshift and blueshift change very quickly, and these are associated with these bright loops that we see in silicon-4. Another example of a jet that we can see around here. We see many examples actually of these jets, and they are, many of them are associated with the RBEs and the RREs that we see in the bottom panel. So in the Doppler movie and in the blue wing. So one particular example of a jet here that is associated with a change from redshift to blueshift in this region here. And this is another example. And we can observe for many regions an effect of the torsional motion, so a change from blueshift to redshift, or the other way around, and the associated heating in this slit yaw data. And when these across the slit, what you see here, so the slit is here, and you see a jet that crosses the slit at this location, and we see an enhancement of signal in both carbon-2 and silicon-4. And this is also associated with the blue-shifted event that is shown here. So you see an enhancement of the line, and also a shift of the line and a broadening of the line. Now I should note that not all the RBEs and RREs that we observe have a very strong signal. So for this observation, we found many examples of RBEs and RREs that cross the slit. So you see them on both sides. We see the same signal also in the magnesium K line. So in the core of the magnesium K line, there's a clear correspondence between H alpha and magnesium K. But we really need to bin the data both in space and time in order to see the signal in carbon-2 or in silicon-4. So you see the effect of binning also down here, where the signal at this location is shown with the point, and the bin signal as the fat line. And this is a similar example, but then for a shift towards the red. If we now go back to the observation at the limb. So here is one example of a spicule, and we can see a clear parabola for all the four channels. And we can only see this in calcium 8 because we know that the spicule is here. So I mean, we could follow the spicule because we know the position from the magnesium line, and then we could trace a very faint signal in calcium 8. So then you may think, why if you see a parabola also for the type 2 spicules, do we now still need to make a distinction between the type 1 spicule and a type 2 spicule? And yes, we do need to do that because we clearly see that there's heating along the spicule for the type 2 spicules, and they have very much higher velocities than the type 1 spicules. So type 1 spicules, they also show a parabolic path, but they do not show the type of failing that we see for the type 2 spicules. So the higher velocities are shown here. So we could measure for the 54 spicules, we could measure the velocity at the rise phase, and they match much more better the observations for the type 2 spicules that has been done before. So there is a clear distinction in velocity between the type 1 and type 2 spicules. So now we go to type 1 spicules, and in particular to the dynamic fibrils that we can observe in active region plage. So in this particular observation, we look at an active region in the lower left part of the sun. And that's important to note because if we look at the H-alpha line core, you see this region with the fibrils that are moving up and down. And up is now in this direction because the sun, or the active region, is located here. So we see the fibrils moving up and down in H-alpha line core, and then we see these bright grains that move more or less in a similar fashion in the silicon 4 slit show data. I remember now that the dynamic fibrils, they move nicely up and down, so we can easily draw a line along the spicule, and then we get a parabolic path. And the simulations have shown that this is an effect of shocks that move up due to upward propagating waves. So now we look in more detail at this region. We see the dynamic fibrils moving up and down. And if you look closely, you can see a number of examples where the bright grains seem to move in similar fashion, but they do not trace the full path that we can see in the H-alpha line, but only a part of this. And this is clearer when we look into the blue wing of H-alpha. So we only see the upward face of the dynamic fibril, and then we compare to the inverted images, and now we can trace what is black here with what is black there, and this becomes a bit clearer when we look at these XT plots. So you see the parabolas for the dynamic fibrils, and for many of them, and we have traced them with the red line, you can see this enhanced emission in silicon 4. And for most of the time, this is during the upward phase, but we also see them sometimes during the downfall phase. It's clearer in a blink like this. And it's not only the ones that are outlined with red lines, but there are more examples where we see the emission in silicon 4 on top of the H-alpha signal. This is one more detail, or this is a detailed view on a few examples. So we look at the H-alpha line core. We see the dynamic fibrils as the parabolas, both in the H-alpha line center and calcium 8542. It's also interesting to note that in the blue wing you only see the upward phase, so you only see half of the parabola, while in the red wing you only see the downfall phase. And now in this silicon 4, you can see this bright emission at the top of the parabola. So this is due to the bright features that move along the line. If we look at spectra, then we can see the sign of the dynamic fibrils, and this is most clearly seen in calcium 8542 because the line is not so broad as the H-alpha line, but you see the characteristic behavior of the blue shift and then the decay towards the red. This can be seen nicely in calcium H, in H alpha, and magnesium K. And then for a number of examples, we see these brightening or the enhancements of the silicon line, which is combined with the blue shift and a broadening of the line. Now, it's important to note that you can only do this when you look along the magnetic field. So basically, the dynamic fiber is moving towards you. Because if that's not the case, then you have a problem with the fact that you look for the spectra at one position, but the dynamic fiber is moving across the slit. So you see the dynamic fiber for this point. You see the spectrum here, the blue shift, and then the decay in calcium H. But for the silicon 4 line, we only see this when the bright grain passes through the slit, and you basically cannot follow the dynamic fiber after that. So this is important to note when you compare spectra for extended structures. This is another illustration where we combine the silicon 4 slit data in a large raster and compare them with the grains that we see in the line core intensity. So there is a nice match between the grains at the intensity of the line core, and for many of them you see that this is a region with a blue shift and also a broadening of the line. So finally, then we wonder whether we see a transition region, a signal in the internetwork. So we look at an observation of a very quiet region, and you see the grains both in all the slit data and in calcium H. So now you may wonder whether this is an effect of the lines. But if you have a close look at the spectra, then you see the grains in calcium H, in calcium H542, and in effect also in H alpha and in magnesium K. But there's hardly any signal in carbon 2 and silicon 4. So we have to conclude that most of the signal that you see here, that is an effect of the continuum. So finally, these are my conclusions. I'll leave them for you to read. Thank you.
Thank you very much. The paper is open for questions. Tom.
Luke, is there a coronal response to these type 2 spicules? I was very disappointed that your picture is cut off and you didn't have like AIA above to see what happened to these spicules.
Yes, you would like to do that, and it has been done before, but it's really hard to do this because of the resolution. So the AIA pixels are so big that this is hard to see.
But isn't there a Nature paper by you guys about this, where you follow by Scott, following it to higher temperatures?
Yes, what he said it's been done.
You?
Sorry again? Oh, the event rate.
Yeah.
I don't have a clear number here, and one of the problems here is that that in order to see them on the disk, you have to go to the far blue wing or the far red wing in order to filter out all the mess, basically, because there are many spicules. And by going into the wing in the blue wing or the red wing, you basically filter out a large number, and you can only select, or you can look at one by one in detail.
I was equally disappointed not to see the connection to the photosphere. So where are the factally related to these attribute cycles, for example?
Okay. Do I have that in a movie here? Okay, I don't have the movie in my talk here, but I mean the region that you see here, so where you see all the dynamic fibrils, that is a region of very strong blast. So basically, there's magnetic field everywhere there. So that is the region in the upper corner here.
Right, but in detail with these high-resolution observations, how are the actual locations of factally connected to these chromospheric transition region effects?
So you mean one by one? If you can trace one bright point with one jet. Well, indeed that is what you would like to do, but it is really hard to correlate. And then I should maybe show this movie. So what you see here. I mean, you can kind of sense that they come from this region, but it's hard to connect it to this bright point or that bright point or that one. Or so in that sense, there is a gap between the bright points and what we can observe in H alpha and calcium 8542.
Lindsay and then Lakshmi.
So you showed a couple of movies further on that there was evidence for possibly for torsional movements in this spiral or jets or spicules. I'm wondering whether, again, another movie further on, there was something that looked like kind of closed. You see, there's spicules which are connecting. Do you ever see evidence for torsion in such structures, or only in the open ones?
Well, I mean, you would be tempted to say that it's going on here too, right? I mean, you see very fast changes from red to blue. But
you analyze that?
No, not in the detail that you can actually track it in time.
Actually?
So I really liked your plot where you showed the parabolas of dynamic distribution H alpha and the shock trends in silicon. But then I was wondering why there is no apparent time delay, because these are shock driven. I would expect that the compression takes some time to kick in and then show up in silicon. But
yes, and that is probably related to the problem that I try to show here, is that you only get the spectrum at one spatial location, and there is an angle here too. So the fact that we can see the parabola here means that there is an angle with the observation.
One brief last question by...
Have you had plans to study the magnetic configuration related to this?
Not in detail. We have kind of the data, but it is, like I said before, it is really hard to correlate one event with what is happening at the photosphere. Yes, it's mostly a unipolar a region. Yeah.
We have to
My question not about spicules.
Say it again?
My question not about spicules.
You can discuss him later. You can ask him later. We have to move on, I think. Thank you again.
Stefan Schmidt, who will talk about full disk variability of magnesium 2H in 10 minutes. Yeah? 10 minutes.
Yeah. Okay, so the work I'll be going into here is really primarily observational work, delving into the variability that we find with the magnesium 2 profiles when we look at full disk mosaics. So really, these are the kind of data sets that weren't available before the launch of IRIS, and I think give us very unique constraints to the modeling efforts that are ongoing. So, working with the magnesium 2 doublet, prior we understood that there was going to be a lot of modeling that was necessary to understand these lines prior to launch. There's this triumvirate of Bifrost papers that delve into the physics of the atoms, and then the forward modeling, the magnesium emission through the atmosphere. Along the same lines, there's the VAL, the semi-empirical atmospheres from Vernazza and Avrid have been expanded to simulate the emission from magnesium 2. With all this modeling effort, it's really been based off a fairly sparse set of magnesium 2 measurements. The most complete we have for actual orbital stuff is OSO 8, which had very coarse resolution, something like 20 arc seconds. And so to do these sort of studies, we need long duration data sets and large spatial coverage. And so these are the kind of things that you can do with an orbital mission like IRIS. So I need to give another plug to the full disk observing program. This predates my time as part of the science team. Scott's put in a lot of work into making this available. So these mosaic data sets are available in both FITS format and in quick look data at the Lockheed website. We take these about once a month. It takes 18 hours to do an observation with 180 separate pointings. It's not a small feat to get this to work, but they've pulled it off. So we have something like a 2 arc second spatial steps between rasters and a third of an arc second gridding in the solar Y direction. So we are actually able to capture fine scale structure with these, although we are somewhat coarse in the X direction. These are 4-second exposures, and we have maps in both magnesium 2 lines, the carbon 2 and the silicon 4. I'll be talking just about the magnesium 2H. But the forthcoming work in the other lines is on the way. So a quick little thing about what the magnesium 2 lines actually look like. These are kind of typical internetwork profiles that we observe. So to actually categorize how to parameterize basically the different parameters of these profiles, we've gone about using a double Gaussian fit that allows us to capture the central reversal. So it's basically a wide amplitude positive Gaussian and a narrow negative amplitude Gaussian to capture the self-reversed core. So the chi-squareds for these profiles are around, reduced chi-squareds are around 0.4. About half of our 4 million profiles that we have within the full sum mosaic fit within the chi-squared limits less than this. So this model actually does a fairly good job. It's not perfect. We've experimented with a few different ways to do this, but we think it's largely effective at capturing, at measuring these different parameters of the line. So the blinking image here has 3 images. We have the intensity at the H3 core. We have the line of sight magnetic field that's taken concurrently with the IRIS raster from HMI. And then we have a single frame from AA 193. Looking at the H3 intensity image, the things that are clear is that there is a strong magnetic sensitivity to the line. You have very bright H3 core surrounding plage. At the opposite end of the spectrum, filaments are very obvious at the H3 core. It appears very dim. So using these maps, we've been able to extract, basically limit down regions of interest, extract out regions that are network, plage, and internetwork, and do statistical analysis on these different subsets. So in the next couple slides, I'm going to zoom into these 2 regions, 1 and 2, which show kind of characteristic quiet sun and characteristic plage. So here are the examples of intensity statistics we see within these 2 regions. They go from the top, we have the intensity at H1V, which is something that's, the structures here are something like reverse granulation or the grains that have been talked about in Carlson and Stein. Going down to below that, we have H2V, which again, so now you can see that network elements and the core of plage becomes very bright in H2V, and there's a very strong contrast with the internetwork. At H3, you can see that the structure becomes significantly more complicated. You can start to see the outlines of fibrils. There's hints of magnetically aligned structure, but specifically in the inner network, it's obviously a very complex magnetic topology. There are 3 other colored pixels in here. Green pixels actually represent profiles which have single peaks. These have been mentioned in the context of flares, and but we actually observe these all over the place within our data set. We also have a number of bad fits and missing data. Our accuracy, or based on a reduced chi-squared of 1.5, we achieve accurate fits for approximately 88% of our 4 million profiles. So you can also look at different statistics of the profile besides intensity. These are widths. We find for the H1 width, H1 separation, there's a very strong correlation with the intensity at H2. The width at H2 is actually a somewhat more complicated diagnostic. There's not a very strong contrast between magnetic concentrations and non-magnetic concentrations, it offers us, it's very obvious that you're looking at very different structures between the width of H1 and the width of H2. And velocity, you can see that there's a large degree of variability within the network. Most of the structure is fairly small, fine scale structure, and it kind of, generally we see flows that are on the order of 11 kilometers a second, 12 kilometers a second. You can see in the core of the plage region on the right that there are a lot of these green pixels. These are the single peak profiles. So here's an example of a number of these single peak profiles. On the left upper hand side is kind of the typical plage profile, typical single peak plage profile. These are about 10% of plage are represented by these sort of profiles. There is a continuum gradient as you go. That you do not just go from very strongly reversed to the single peak. The profile in the middle left is an example of one of these, the gradients that you see where you have a very mild, very weak H2 separation, but you do actually have a core there. The bottom is a sunspot profile. These are similar to the profiles that were, there's a Lights paper from 1981, I believe, that observes umbral profiles. These are significantly dimmer and significantly narrower than plage profiles. We do also observe single peak profiles within the inner network. These are fairly rare, something like 2 or 3%. You can see this profile in the upper right-hand corner. There is the hint that there is the self-absorption feature. However, it's just blue shifted, and so you do only get a single peak for these profiles. The bottom 2 right profiles are kind of represent extreme examples of what we observe. It almost looks like the middle profile that the entire blue half of the emission line has been absorbed, and the lower profile we see something that, again, you just have a single peak here, but generally the magnesium 2 line is now an absorption feature. As I said, there are limitations to our fit model. We have something like a 80 to 90% accuracy. We do better in inner network than we do in strong magnetic fields. Generally, the majority of these are chi-squareds around 1.5, which is what we use as the cutoff. Generally, the residuals are dominated by the region between H1 and H2. Basically, the change in intensity is too abrupt to be captured by Gaussian profiles. So about half of our bad profiles are caused by this. We also have a problem with flat cores and strong asymmetries, as well as profiles that are extremely bright. So the table here lists kind of the general trends that we've captured in terms of the average quantities in inner network, and plage. There's also strong variability within these magnetic structures, and so the idea is that this variability we observe must be tied to the dynamics, the kind of dynamics that Luke was just talking about. So I have an example of a sit and stare profile, again showing one of these shock profiles on the right. The idea is, so within our ensemble of 4 million profiles, we should be able to disentangle how these sort of dynamic effects cause correlated effects throughout different parameter quantities. So what we've done is that we calculated a cross-correlation matrix that allows us to measure how the different parameters of the profiles vary in unison. What we find is that there's a very strong correlation between the velocity at H3 and the asymmetry of H2. That's expected based on our double Gaussian model, but based on the percentage of quality fits we get, we believe that this is actually a physically significant finding. We also find that there's a very strong correlation between H1 and H2 width. And again, the physical root of this may be tied to opacity effects, or this is work that's ongoing and comparing with the atmospheric models. One more note on comparing with the atmospheric models. One thing that we've gone and calculated the center to limb variation in for all of our profile statistics. I won't go into too much detail, but I'll show the one particular one that is slightly at odds with the models that we have. We actually do detect a limb darkening effect at H3. The current semi-empiric models predict that there should not be a strong limb darkening effect at H3. So this implies that maybe there's that these sort of measurements actually can act to help constrain our models for the solar atmosphere. I had to throw one last thing in here in terms of dynamics, and we've talked a lot about how shocks affect these sort of profiles. It's very obvious that magnetic structure plays a large role. Here we're looking at a scan through the magnesium core in a very quiet sun and comparing that to plage. You can see the magnetic structures that are brought out by these differ significantly from magnetic region to magnetic region. And these the magnetic topology invariably plays a role in the structure of the profiles. So that's my last slide. As you've noticed, I have not talked much about the radiative transfer. That's kind of the stuff that's in the works, and yeah, that's everything. Thank you.
Thank you very much. Questions, comments? Marcus and Lakshmi.
How field aligned are those structures you see?
So, Jort's done work on trying to do these sort of calculations with H alpha. It seems apparent that the structures we can see in at least in plage and in the H3 core are above the beta equals 1 region, and you can track linear features that appear to be magnetically aligned. But so you need to compare these with magnetic extrapolations, and the non-potentiality of the chromosphere kind of makes that point almost moot. So how to actually bridge that gap is something that I think we need to think about as a field, probably.
So you showed that as the magnetic field increases, you have a weaker self-absorption or the reversal. So we translated to saying that the weaker fields are hotter, or they are heated close to the photospheric layers, but above the layers, the chromosphere where the core of the magnesium is formed, it's basically cooler atmosphere. But you have, when it goes to the stronger field case, you have basically heating going on till maybe transition region. That's where you see no reversal. How does it compare with self-absorption?
So it's undoubtedly, or I think it's very hard to argue that in magnetically strong regions that the heating is undoubtedly occurring lower in the atmosphere. It's not quite a one-to-one effect because it also matters where your tau equals 1 layer is. It's likely that layer is being pushed lower within plage, and so I think you're seeing a brighter source function, but that's probably occurring lower in the atmosphere.
Any other questions? Could you go back one slide to the limb darkening effects?
Oh, this one. Yeah.
So you show there the H3. Do you see any center to limb effects in the other parameters?
Yeah, no. So it's clearest.
That's what you want to go for.
Yeah.
Full distance.
No, so we have you see. For the semi-empiric models they find that there is a broadening at H1 in center to limb. We find that same effect. We haven't done a side-by-side quantitative comparison. There's a lot of stuff you can do with this, I think, and so using this data to further constrain the models is kind of the conversation we need to begin now.
Any other questions, comments? That's not the case. Thank you again. I invite Thiago Pereira to talk about the magnesium B triplet lines as a diagnostic for heating in the lower chromosphere.
probably move to this side. Would you prefer to walk around? Yeah, maybe.
There's more to the iris magnesium lines than just H and K. And there's interesting diagnostics they can be used for. So this is an iris mean spectrum. You will become very acquainted with it. There's the K line, for example. We've done quite a bit of work on it. There's all these different features, and they can be used for different diagnostics. But also, around the same region, there's some lines, 3 lines. There's a triplet of lines. This one here, and here, there's actually 2 lines. When you observe with the iris spectral resolution, they appear to be blended as 1 line. It looks a bit odd if you look at it carefully, because it looks some kind of a broad line. There's actually 2 lines. And these lines are a triplet of subordinate lines that have some extra diagnostic value. And we try to find out from the point of view of the simulations what they can be used for. So what is the origin of these lines? So if you have here, this is a simplified model atom of magnesium-2. And this level here is the ground level of the H and K line. So these 2 different transitions. They just have a slightly different upper level. And then from this upper level, there's these 3 transitions. They have a very similar energy. Therefore, they are almost in the same position in the spectrum. And if you are acquainted with the calcium-2 atom, this is actually very similar to the calcium H and K and the calcium infrared triplet lines. So they share the same upper level and lower level of these lines. Now, when you look at observations of iris, for example, here we have a raster. Not so interesting, quite sun limb. This is the intensity of the raster in the wavelengths of these 2 blended magnesium lines. This one here. And so this dashed line is the spatially average spectrum. So here the lines seem just like another absorption line in these wings. They're not very interesting. But if we look at the spectrum at one specific position, for example, here, we see that they look quite strange. They become emission lines. And in this case, it's quite peculiar because it's not very common to find these lines in quiet sun in emission. There's a lot more examples. This one is what could be described as element bombs or some other kinds of bombs in the active region plage, where you have a magnesium K line gets strongly enhanced, and these lines also get very enhanced. And also, for example, in the sunspot, there's this one here, this yellow line on the light bridge. It's quite interesting because the magnesium K line looks almost normal, but this line gets greatly enhanced. So there's lots of observations. This one isn't quiet sun. Again, only a small emission. This is a minority. This is very rare in the observations. But it can be used as an extra diagnostic. And we wanted to find out what triggers this emission in these lines. What can you say about the emission? So we use the Bifrost simulations. This is a cut in the simulation in the log of temperature. Everything that is white or saturated is above 50,000 degrees. So the region where the magnesium lines typically form is in this blue area around here. And this is the simulation that has been published. There's a lot of work with it. And we also wanted to try some more exotic simulation. So Vigo kindly provided this simulation of flux emergence that has some little small flaring happening. And so we also calculated the magnesium profiles. Again, using the same model atom and the RH in 1.5D approximation. So this simulation is the same. The height scale was the same. So the height scale was about the same as 16 megameters, but it has a very different density profile. So from the quiet sun simulation, this is how the mean spectrum looks like. We have magnesium in all the other lines. And in white, I have the height of tau equals 1. So the typical mean formation height of the lines. And you see here that the K and H line go almost to 2.5 megameters. And this subordinate triplet, this one and around here. It's kind of unremarkable, around 1 megameter. It's not that different from the other lines around here. This is in terms of distributions of height formation. So we have here different parts of the K line. So the K3 is this absorption central reversal, the K2, the high peaks. And these two are wavelengths of the triplet lines, or the subordinate lines. This is in a height scale, and this is in a column mass scale. And you can see that they nicely complement each other. So they cover a wide range of column mass scale. And I should point that in terms of the classical 1D models, this line, these triplet lines, are formed just around the temperature minimum, the classical temperature minimum, or a bit above. So this is a formation panel. There's lots of information here. But what I wanted you to retain was that in this top panel, we have the source function, and then the bottom panel, we have the contribution function to intensity. Here in this dashed line, we have the source function in the line core, and then this dotted line is essentially the LTE source function, or the local temperature. And this bottom panel is the spectrum. So this white line is the spectrum at one particular location in the simulation. The dashed one is just convolved with the iris resolution. You see from the source function, it starts a bit higher, so this is height. Source function starts higher, at some point it decouples from the local temperature, then goes down, and so you have an absorption line, because the source function gets higher in the wings than in the line core. And this is what happens in more than 99% of the cases in this quiet sun simulation, a simple absorption line. However, at some points, you have a bigger temperature increase. So for example, you see the temperature in this one goes to some kind of local minimum, and then there's a strong increase in temperature. You see this bright area in the source function. So what happens here is the source function is only loosely coupled to the temperature, but it follows some of this increase. So it goes down and then up, and therefore it forms an emission line, as you can see here in the spectrum. So in this case, it looks almost like one of the H or K lines. So what seems to trigger this is a temperature effect, that you have a large temperature increase between the region where the wings of these lines are formed and the region where the core is formed, which is, again, slightly around the classical temperature minimum. And when you have a strong temperature increase in this region, the line becomes an emission line. And I didn't show here an example of the flaring simulation, but it's pretty much the same mechanism. And we try to go a bit farther to see, can you actually derive some meaningful thing other than just saying that some heating or some heating went into this location? So we tried to get an observable. Here, this is the ratio of the core intensity over the wing intensity of this triplet line. And this is a temperature difference between where the wings are formed and where the core is formed. And then these triangles, in fact, I have the source function in brightness temperature units. So this shows a more or less linear relation between the increase in intensity and increase in source function, which is more or less what we expected, because Eddington-Barbier holds for this line. So this just tells you when the intensity increases, or when the source function increases, the intensity increases. And you can kind of measure the temperature difference in the atmosphere by that. But of course, you don't really measure the source functions, you have observations. So you want to know, how much am I missing? And this is what the yellow points show. So you can still recover the overall figure of between the ratio of intensities, but there's a lot of scatter in this is actually the true temperature difference in the atmosphere. So you can derive some relation, but it's not the tightest fit. So we just need to keep that in mind. Another question is, okay, fine. You have a temperature increase in the atmosphere, but how likely? There's lots of temperature increases in different points. What are the actual conditions? What else do you need to have emission in these lines? And again, we looked at this. This is a distribution of all the columns in the simulation in yellow. And in blue, you have only the columns in the quiet sun simulation that show emission. And this is, again, the same temperature difference between these two regions, and this is the electron density. And from these distributions, you find that they are more or less clustered around this region. So you need a temperature increase of, say, at least 1,500 degrees and an electron density of around 10 to the 18 electrons per cubic meter. So in summary, there's interesting diagnostics that we can use for these lines. And the only thing I want you to retain is that this line is going to emission when you have a temperature difference of at least 1,500 degrees, and the column mass is slightly above the temperature minimum, and relatively high electron densities. Thank you.
Thank you very much for this beautiful talk. I'm sure there are questions or comments. Tom? And then Tom.
It was mentioned earlier that there's Lyman data pumping of the upper levels of magnesium 2. Did you consider any kind of radiative pumping mechanisms that might produce these same effects?
We include a bunch of lines that contribute to bound-free transitions that might affect this region. But aside from what was said before, that the tests that you already made, we didn't do any extra additional modeling of of those bound-free transitions or other transitions that could influence these lines.
Yep.
The heating of the lower chromosphere, this should be also visible in ultraviolet continuum, far in the channel. Did you try to for some correlation between subordinate lines and FUV continuum? So the formation rate should be similar to what you said.
No, I did not. And as you know, it's difficult to observe the true continuum in the FUV with iris because the count rates are very low. Well, you can see, say, for example, here. You can see even the photosphere continuum in this region is quite enhanced in regards to the average continuum. And you often see that. And something I didn't say was that you can also, from the shape of the emission, when this heating takes place very deep in the photosphere, so the source function increase takes place deep, the emission goes mostly in the far wings of the line, and the core of the line looks more or less like the average. And so you typically see a high continuum intensity around the NUV, but in the FUV I didn't study.
This enhanced wing or continuum, right? Is this photospheric or slow photospheric?
It's mostly photospheric. Well, depends on what you say is the photosphere, but say 400, 300 kilometers.
Other questions, comments? If not, I may have a question and a comment. The comment would be, it's refreshing to see graphics that were not produced with IDA. And the question is, what software did you use for these fancy transitions?
The IDL free zone. No IDL was used for this. No, it was used Python and the plotting package called matplotlib.
Setting new standards here.
With all the iris data was processed with that.
Okay, that's true. This is a special pipeline. It only runs in my computer.
Other questions, more serious questions. Comments? If this is not the case, thank you again. And before, oh no, we have another talk.
That's the introduction.
Yes, I guess watch that. Okay. Plug in first. We have another talk. You see it on there? The clock. Do you see it, or should I move it somewhere else? No, I can see it from here. Yeah. That's it. Oh, yeah, that's a long title. I'm not sure I should read it. You will see it now. You can shorten it. Actually, it's a different title. This is a different title than in the program. But anyway, the floor is yours.
Yeah, thank you. I would like to present some data and findings from two joint observations between IRIS and NST, and they focused, and the studies focused on the sunspot observations. And here's an example of the data set that we used. It's a sunspot observed near the center of the solar disk. And essentially, you can see a lot of different dynamics and flows. But basically, I would like to focus on these oscillations of intensity that we observe, as well as the umbra flashes that occur everywhere, not everywhere in the umbra. Also, I would like to note this very small streaks or oscillating jets that were recently observed in different sunspots and by Luke and co-authors. And I also would like to notice that this sunspot has been studied by several people, and Tian studied shocks, formations, and oscillations in the umbra, and also Burnett with co-authors studied downflows, and Lucia Klein also studied downflows about the umbra. So this is an example of IRIS data for the same sunspot, and what we have on the left is variations of the spectral line, silicon-4 and magnesium, as a function of time. This is about 30 minutes of observations. And this location is somewhere above the sunspot, near the center of the umbra. That location is about the penumbra, and this is outside the sunspot. And obviously, we can see the different behavior of those spectral lines and oscillations of intensity. Those profiles that I plot here are intensity oscillations or intensity profiles along this dotted line. So essentially what we observe here is formation of shocks. And what is interesting that if we follow the intensity and periodicity or period of the shocks, they are not equal and change in time. We have period of time when shocks are very strong, and basically their period or distance between the shocks is higher. Then we have period of times when they are very weak and occur often. When we look at the transition region, we also see that shocks are formed. However, again, intensity and time variations are a little bit different. They're kind of more stable. The amplitude doesn't change that drastically as it happens lower in the chromosphere. Also, what is interesting that, as I noticed, this variation occurs not only about the umbra. When we look at the penumbra, here shocks are still kind of visible, but much, much weaker. But there is strong and about 20 minutes intensity oscillations, these long-term oscillations, which are not really visible in transition region. So we would like to, and what we wanted to do, just to see how this pattern changes across the umbra, for example, if it's the same at every pixel of the umbra or not. And what IRIS observed, this is the slit of the IRIS spectrograph, and this was sit and stare mode, so there was no scanning, and very, very high cadence, about, I believe, 3 seconds or so. So we can produce those kind of profiles for every pixel along this image and see how this shock pattern changes. But before I will go to that, I would like to show the whole interval. It's about 90 minutes or so, variations of intensity using IRIS data at 1 pixel. So again, what is interesting, this magnesium line is in red. The intensity is much weaker. And the silicon line shows a little bit different behavior. At some point, at the beginning of observations of this run, the intensity of those shocks were more or less the same, but then suddenly silicon lines show different behavior, and then apparently it changed again. And that appears to be about 20, 30 minutes, some kind of oscillations, not oscillations, long-term periodicity in that behavior, which is not really, well, at least I couldn't find a reasonable explanation why such a variation could occur. Also, it's interesting that the time delay between those two lines, average is about 15 seconds, which is very similar to what Tian determined. However, when you look at this time interval in details, you can find that some of them, sometimes the time delay is much shorter, actually 0. Sometimes it's much longer, about 40 seconds, and at some period of times there is no really very well any correspondence, although we can say that in general there is propagation of waves from the photosphere up in chromosphere in the transition region. However, there is something else which probably could be, for example, reflection of the waves from the transition region back, and that pattern could be the result of that interaction. So we can use those time profiles, and at each pixel we can calculate, for example, power spectra and see how those oscillations differ. So we have, this is NST H alpha plus 0.4. This is NST H alpha plus 0.8, and 2 iris images. And what we did, again, for each pixel, we calculated power spectra, and here we plot a stack of power spectra. So this is frequency domain, and this is distance along the slit. So this is for silicon, for magnesium, and H alpha. So what interesting is that we start from here. At a certain point in the middle of the umbra, essentially no oscillations are registered in the transition region. As you see, essentially power spectra is very weak, or compared to that part is non-existent. At the same time, when you look in magnesium line and the chromospheric line, we see that the oscillations, power and intensity of those oscillations across the umbra doesn't really differ or change too much across the penumbra. So essentially, what probably happened, something happened at the transition region level that those oscillations are not as strong or disappear. And one of the guess or suggestion that it could be, when we look at the data in AA, this quadrant of this umbra is the same thing here, has strong horizontal fields, kind of starting from the umbra and moving, actually connecting somewhere to the center vector region, so which probably may have something to do with that absence of oscillations, or absence of power at the transition region. Although, what? So we also look at the structure of umbral flashes, in this sunspot, and those umbral flashes appear repeating at the same time. So we take the time series and actually draw a line along the position where the umbral flashes appear, and then we all reported those lines. And what happens is that umbral flashes, strong one, appear at the same location in active region in the penumbra. And what was interesting that they tend to appear next or near umbral light bridges inside the umbra, because those structures are light bridges. And moreover, umbral flashes tend to appear on that side of light bridges that face the center of the sunspot. So we speculate that, how is it 15 minutes?
I'm not changing the frequency.
Anyway, one second. here we show 2 minutes of evolution of those umbra flashes, and you can see that they start at some point along the light bridges and then form lanes inside the sunspot, and those lanes repeat. So essentially, they are not occurring and anywhere inside the sunspot, but at some preferred positions, and that's. My time is up. So what I intended to show, that light bridges apparently appear to be very important for heating of transition region, and the loops, coronal loops that start the light bridges and appear very bright in that area. So why umbral flashes tend to occur at the light bridges? There is some explanation on the screen. However, there's something maybe interesting and to discuss and understand. Thank you.
Thank you very much. Questions? Comments?
Okay.
Bart.
You were talking about the lack of correlation between, or sometimes lack of correlation between magnesium and silicon. Is it possible it's a similar mechanism as to what Luke pointed out, which is that, I'm presuming this is sit and stare observations, that you actually do have a transition region response, but the field is no longer vertical right underneath the slit as now maybe for a certain time period. The incline, so the shock response is actually next to your slit and you're not actually observing. In other words, that you're no longer looking at the chromospheric and transition region
because of the
field line,
because the field lines are inclined. It probably could be one of the explanations that's the reason. If we think that field lines inside the umbra can, very quickly change their directions, but this is something that has to be probably we look more carefully along the slit. So if this delay happens everywhere, maybe along the sunspots, that could be an explanation. However, if you find areas where the field is predominantly vertical, that might be harder to explain. However, it does change. Yes, that's another solution. All right.
Jean-Claude?
Yes. Do you confirm, it seems that you do not confirm the oscillations observed in carbon-4 with SNL at periods about 150 seconds. I didn't see, when I looked at your frequencies, I didn't see these values.
150 seconds?
150 seconds around there. In both velocity, density, and so on.
Actually, those shocks, their period might be in this range, 120. Some of those shocks you observe, they show a period of 2 minutes, which is 120 seconds, or 180 seconds. And also those little jets that I showed at the beginning of the movie, their periodicity is about 150, 120, between 2 and 3 minutes.
All right. Other questions? Points? That seems not to be the case, so thank you again.
Thank you.
We have one final presentation. Before we go to lunch, Mark Rust will talk about some decist stuff.
So I don't have a presentation. I really have an invitation. Thanks for the organizers for letting me do this, and apologies for delaying lunch. Really, I'm just going to try to quickly show you the status of the DKI solar telescope very quickly, and invitation to participate in the critical science plan. So briefly, a status report, what we're planning for the critical science activities, and a call for your participation in this. So just real quick summary, of course, the DKIST is a 4-meter aperture telescope, off-axis telescope. It has adaptive optics.
sits in a site with chronographic capabilities, particularly in the near infrared, is planning high precision spectropolarimetry, and will host a suite of instruments run in sort of a service mode style, and is currently under construction. This is some time ago, some 6 months or so ago. The telescope is coming along. This is an image similar to the model here from the same angle. You can see that this is the height of the Coudet platform. This is just today off of the webcam. You can see that the first ring for the dome is installed. They're starting to put up the dome. The dome will be finished in about a year's time, and operations begin in September 2019. Of course, there's lots of progress off the mountain as well. This is the telescope mount assembly. It's a movie, but I'm not going to take the time to play it. I can show you later if you'd like. The Coudet table. These have been disassembled and taken to Hawaii. This is the M1 mirror being polished, and the polishing is ahead of schedule. So the telescope will host a series of instruments, an imager, a visible broadband imager that the NSO is building, but lots of partners are involved, of course. There's a University of Hawaii is building a cryo near-infrared spectropolarimeter and a diffraction-limited spectropolarimeter with the PIs Jeff Kuhn and Hao-Xing Lin. There's a VIS being built here at the High Altitude Observatory. VTF, visible tunable filter, and some MCAO development is occurring at the Kippenhauer Institute. And there's a consortium in the UK that is building the cameras. This instrument suite is very capable. The instruments can be used independently and together. This is just a schematic of the wavelengths overlap. This is the VISP that can observe effectively at any wavelength. These instruments, other instruments, all have pre-filters, so they're connected by quite a intricate beam splitter configuration. And so the issue for when you think about this telescope for science is how to combine the instruments to effectively do the science that you want to do. My role in this is really to try to help the community organize to develop a critical science plan before first light. And really the aim in there is to be ready as a community by science first light to execute a set of observations that take advantage of the telescope capabilities and to address critical compelling science. And what I've done here is just very crudely put together a sort of a timeline for what we would want to do. As a community, we want to understand the capabilities and define the science goals and see how those couple together. We're going to try then to compile a set of science use cases, coordinate these into a set of teams, convert those use cases into real observing proposals to run in the first sort of year or year and a half, 2 years of observations. So perform those observations based on those observing proposals, and then employ that data for science and publish the first light results. That's a rough outline of maybe the sequence of events that are between now and September of 2019. This process will likely be iterated. This is intended as a helpful but non-rigid framework, and of course the science will evolve. One of the reasons we're getting started on this is that this critical science plan helps the project beyond the science definition. It helps the development of operations and data management tools, and to get those operations and data management tools right is going to help us use this telescope when it's online. Also, the CSB process is not exclusive. Everyone's welcome, nor is it unique. There's going to be other proposals submitting options. A normal standard submission and review process will be in place as well. But if you would like to get involved in this, and I hope you will, we've put together a website which looks like this, but is hard to see. on the screen. But it basically defines the critical science stand process. It defines some research areas. For organizational effort, it has some description of what those research areas might include. Under those research areas, there's some topics, and each of these topics has a person that might be useful as a point of contact. It has descriptions of the instruments in detail, and has some tools, descriptions of the beam splitter configuration to combine those instruments, and a tool to evaluate how effectively you do that. And then finally, it has a science use case submission form that tries to carefully outline both what the project needs and what you might want to think about to do science with this telescope. Please, if you're interested, go there. If you need help, or there's the use case submission form is password protected. I can give you that password with no difficulty. It's just to prevent spamming. One other thing I'd like to mention is we've talked a lot with the NSF of how to facilitate work in preparation for DKIST. And one of the difficulties that the NSF faces is that often proposals from the solar community come in a few at a time. And so there's an inability to, their review panel breakdown really reflects the volume of proposals that come in. So the NSF actually welcomes sort of a critical mass of proposals, 15 to 20-ish, so that they can make a topical review panel. Of course, they have the caveat that the proposal success rate is low, but if we as a community submit something on the order of this number of proposals for science, for solar science in preparation for DKIST or otherwise, okay, then the NSF is willing to formulate a review panel that perhaps has more a larger knowledge base for review. Of course, timing is critical. The proposal windows are really between September and November each year, and this is really the NSF's bottom line. They encourage the community to sort of self-organize in order to get this kind of work funded. I'm willing to serve as a contact point. I don't have to, of course, but if we want to coordinate this in some sense for this fall or any following falls, we can do that, and the NSF welcomes it. Again, this is they're really trying to have a set of number of proposals that come in that allow this kind of review panel to be formed. Additionally, it's hard to take in this suite of instruments and their capabilities through a web page, and so we're planning a series of workshops, perhaps the first being at the SBD in 2016 here. Again, the web address is here, my email address is here. This is an invitation to really get involved. It is 2019 that we're talking about, but I think in order to put some compelling science together and to convert that science into real observing proposals that can be run on the telescope with the instrument suite that's being planned, it's a good time to start. Thanks.
Thank you, Mark. I'm sure there are a couple of questions. Ted, did you have one?
I'm curious about putting it all off until late 2019. Our satellites are not getting any younger. And I think it would be very interesting to have some use cases with joint observing with IRIS and Minode. Can we propose something much sooner than late 2019?
So no, I'm sorry, that's a misunderstanding. I'm asking you to get involved now. The telescope will not become operational until September 2019.
No, he's asking about NSF proposal, right?
No, NSF proposals can occur in preparation for DKIST science. That's what they're asking for. They're asking for them now in preparation, so to do science now so that we can know what we want to do in 2019. So I'm sorry I gave the impression that we're putting anything off. Only put off till 2019 is completion of the telescope and the instruments. That's the 2019 date. Everything else needs to happen now and in the years intervening between now and 2019. Does that answer your question?
Well, that's part of it. Will there be any opportunities for joint observing before 2019?
The telescope will not be observing until 2019. Okay, the completion date for the telescope is 2019. Okay, so I guess the short answer is no. But there are opportunities in terms of doing science with current instrumentation, proposing that as either on its own or in preparation for possible DKIS science, and defining that science for 2019 with resources that the NSF is willing to put behind that now. Okay?
I have a question about proposals.
Yeah.
Say if you submit a proposal in this field, when proposals will be considered?
Yeah, so the others, I need to jump in here. The NSF schedule is some reviews proposals. They generally call for them in this kind of time period, and then they review them. My experience is over the next sort of 6 months. Okay, this is not a guarantee that they will fund those proposals. This is an indication by the NSF that they're willing to convene a panel that has solar expertise on it to review those proposals, which currently right now does not occur when you submit to NSF AST. There's people from all of astronomy reviewing the solar proposals. So this is a way for the community to review the proposals and say these are really compelling solar physics proposals. If we can get a critical mass of proposals submitted.
There will be 14 proposals, then they will not be considered?
So there'll be 15 to 20-ish proposals.
If less than 15, like 14 proposals.
They will generally have a success rate of about 15%. Okay? But that's,
yes, please.
Yeah.
What's the point of, like, programmatically of submitting to the AST when we could just submit to the STP program in the GEO, whatever it's called there, that they don't have panels? And I guess why are you encouraging to submit
NSF AST has an interest in making sure that DKIS science is done and done well. Okay? Okay. And so they're asking the community to self-organize to submit proposals of science that are potentially relevant to the DKIS era. Yeah.
If they have an interest in the community getting involved, why don't they just have an announcement of opportunity with a specific DKIS science?
The answer that I've gotten is that we do not do AOs, okay, for particular instruments. And I think the real issue is if they do an AO for DKIS, they will be doing an AO for all their other major projects, okay? So this is as close as they're willing, this statement is as close as they're willing to get to an AO, okay? And that was an explicit discussion with the program manager, okay?
With these clarifying words, thank you again.
Thanks.